Hello, aspirant. So far, we have seen different analytical techniques, including the liquid chromatography techniques. In this module, we are going to see gas chromatographic technique and also the application of gas chromatography techniques. We will see the gas chromatography technique in detail in the upcoming slides. Gas chromatographic technique is one of the widely adopted, widely used analytical technique in pharmaceutical as well as non-pharmaceutical industries, including chemical, petrochemical, as well as agricultural, other industries. And the application of gas chromatography is wide and it is being used for the analysis of impurities and environmental sciences, etc. So basically, the gas chromatograph is an analytical instrument that measures the content of various volatile or gaseous components in the sample. So either you can analyze the gaseous components, volatile components. Basically, you have to make the component or compound volatile and mix with the gaseous mobile phase to get eluted and analyze that particular sample. Gas chromatography is a common type of chromatography where the mobile phase is always gas and the stationary phase is either solid or liquid, which will be used to separate the compounds. There is two types of gas chromatography, that is gas solid chromatography GSC, where the stationary phase is solid and it is useful for the separation of various compounds, including the gases like CH4, CO2, CO, that is carbon monoxide, carbon dioxide, methane, etc. And this is the most commonly used gas chromatographic technique with the solid stationary phase for the chemical compound, semi-volatile and volatile compound separation and analysis. Another technique is the gas liquid chromatography where the stationary phase is liquid and it is being used for those compounds which is having very low volatility, and it is being used for the separation of volatile species, and the stationary phase is having the low volatility so that it can be used for the separation of volatile species. So the stationary phase will not easily volatile and it contains the compounds which is volatile very easily. That's where it is being used for various applications. What are the importance of gas chromatography? Why gas chromatography is required? So basically the molecules or compounds which are volatile in nature, it is very difficult to analyze in analytical techniques like HPLC or any other technique. So those compounds which are easily getting volatile like solvents which is having very low boil point, etc., can be analyzed by gas chromatographic techniques. And the applications also involve the volatile compounds like peppermint oil, clove oil, etc., can be quantified using the gas chromatography. The oil content and assay of volatile compounds shall be analyzed by using the gas chromatography technique, and the impurity like methanol, dichloromethane, and chloroform, which is having low boiling point, as I said, can be analyzed by using gas chromatography. And these applications are inclusive of medicinal formulations as well as other products. And gas chromatography also used for extractable leachable analysis where you need to analyze volatile organic impurities and semi-volatile organic impurities. What is the principle behind the gas chromatographic technique or how it works? Basically, the sample solution injected into the instrument enters into a gas stream. So the sample is mixed with the gas stream. Then it transports the sample into the separation tube known as column. So basically the mobile phase is gas and the sample is introduced into the gas and both are entering into the column. The gas generally is a carrier gas. It can be helium or nitrogen. And the components of the sample will be separated inside the column based on the partition coefficient or miscibility with the gaseous component as well as the affinity towards the column component. Finally, the detector measures the quantity of the compounds at the exit of the column. When we measure a sample with an unknown concentration, parallelly, a standard sample with a known concentration also injected in the instrument. So then the standard sample peak retention time and the area is compared with the test sample to calculate the concentration. So basically you inject a standard. So the interest, the compound which is we are going to analyze, the standard for that particular compound also will be injected. So then the peak area of the standard will be compared with the sample, then the test sample concentration will be calculated. So the gas chromatography will be used for the qualitative analysis. So basically when you compare the retention time, when we find both are same or different, then it is the qualitative analysis. This is basically the identification. Then when you compare the peak area, it will be a quantitative analysis where it will give you the concentration of the compound in the particular sample. One more point we need to consider or we should know that the stationary phase, that is the column which is used in the gas chromatography, is always stored in a column oven where the temperature ranges from 40 degree to 280 degrees centigrade. Since this kept inside the column oven so that the volatile nature of the compound is maintained when it transported through the column. So we already seen that the carrier gas, whether it is nitrogen or helium, will be used as the mobile phase. Then there is a auto sampler which inject the sample and introduce the sample into the column. And based on the nature of the molecule, the column will be selected and also the detector will be selected based on the sensitivity of the compound, whether it is microgram or nanogram level we want to analyze. Then finally, once the compound is eluted, there will be appropriate software will be used for the integration of the peaks which is detected, and eventually the qualitative and quantitative analysis will be carried out. This slide shows a schematic representation of a gas chromatographic instrument and the different parts of the instrument. So this is the carrier gas tank through which the mobile phase, the gas will be delivered through a pressure regulator and a flow controller, through which the gas flow will be constantly released, and then it will be mixed with the sample which is injected through the auto sampler on the injection port. And both mobile phase and sample is mixed, and the entire setup is inside the column movement so that the sample gets volatile in this particular area so that it is easily mixed with the gas and it is passed through the column and getting separated. The components which is separated is detected through a appropriate detector, whether it is FID or mass, and then the detected compounds will be processed in terms of a chromatogram where you can find the retention time on the peak area, and also the gas will be delivered through the outlet. This particular slide showing a image of a typical gas chromatographic instrument. which is containing a auto sampler unit above the instrument, and then all other parts are packed inside the entire instrument. And you can see a monitor here. You can control the various parameters of the instrument, including the column temperature, auto sampler temperature, etc., and the flow of the gas, etc. This slide showing another gas chromatographic instrument with a headspace auto sampler. In the previous slide, what we have seen is a auto sampler which is used for the liquid samples, and here also this auto sampler, headspace auto sampler, will be used, and this headspace auto sampler is generally used for the highly volatile compounds, and you can apply the sample directly inside the headspace auto sampler vial. So the samples will be directly taken to the vial, and in the headspace the sample will get evaporated, then it will be injected into the vapor of the sample will be injected into the column along with the mobile phase. So this is the most commonly used instrument for the analysis of volatile organic compounds, including the solvents which are having the boiling point, low boiling point. So in this slide again we are seeing how the gas chromatographic technique is working in general. So basically the sample is injected into a heating block where the compound is readily vaporized, and the sample vapor is carried by the carrier gas into the column inlet. Then the solute is absorbed in the head of the column by the stationary phase, and it is traveled at its own rate through the column according to its partition coefficient value. Then the solutes are eluted according to their partition coefficient and entered into the detector. In the detector, solutes gives a series of signals resulting from the concentration changes and the different rates of elution. So you have the retention time and the peak area based on the concentration of the sample and based on the eluting pattern. Then the recorder provides a plot of the time against the composition of the carrier gas stream, and the peaks of the plot give the quantitative data of the in the gas chromatograph. So this particular working procedure we have already seen in the previous slides also, but here it is sequentially explained. This particular slide showing a typical chromatogram of a gas chromatography. So you can see the elution of compounds from the start of the time, and you can see the elution of compounds here at 4.5 minutes, then 6 minutes, then 7.5 minutes and 9 minutes. Different compounds are getting eluted. These are basically volatile or semi-volatile in nature, so that it is getting vaporized and mixed with the gas and getting eluted through the column. Now we are coming to the components of gas chromatographic instrument, which we have already seen in the schematic diagram also. So a gas chromatographic instrument will have the following parts. That is, now one is the pressure regulator, then the sample injection port, either it can be a ALS or a headspace, then gas chromatographic column, then a stationary phase which is contained inside the column, then the detector which is mass detector or FID detector or some other detector, then finally a signal recorder or a integrated software. The first one is the pressure regulator, which is used to adjust the pressure within the limits of 1 to 4 atmospheres, while the flow control valve measures 1 to 1000 liters per minute of the gas. So pressure regulator and the flow controller are most important parts to control the gas pressure as well as the flow. The flow valves are adjustable by a needle valve mounted on the base. The preferred carrier gas may be helium, argon, nitrogen and hydrogen due to their high thermal conductivity. The next is the sample injection port. So basically the samples are injected by a micro syringe through a self-scaling silicon rubber septum in a heated metal. The metal block is healed electrical heater. We used different sizes of injection ports for the injection of a sample. Then auto sampler, there are two types of auto sampler available in gas chromatography, that is auto liquid sampler ALS system, then headspace auto sampler for the direct sampling of for the volatile organic compounds. Now coming to the gas chromatography column, it can be made by tubing coiled into an open spiral. So it is a tube, a spiral tube coiled into spiral in the nature, and copper or stainless steel of for higher temperature is used in the operation. So the spiral coiled tube is made up of copper or stainless steel to manage the high temperature generally involved in the gas chromatography. Then the velocity of the carrier gas flow rate depends on the inner diameter of the chromatographic column and the total length of the column, usually 2 meters. The column will be packed with fused silica, considered to be the purest form of the glass, and metal oxides, Lewis acid sites, and containing hydrogen bonding groups. The stationary phase also cross-linked polymerized material and bonded to the surface of the column to provide a high degree of stability which can result in lower bleeding of the stationary phase. So there will be fused silica packed inside the column which is containing metal oxides and for the hydrogen bonding groups, and then there will be a cross-linked polymeric material which is bonded to the surface to provide the stability to the column, which can prevent the bleeding of the column. Then finally, the elution of the compounds from the column will be vary based on the vaporization temperature. So the retention time of the compound will be varied, identified and detected through the detector. The important part of the gas chromatography is the detector. The most commonly used detectors are flame ionization detector FID and the thermal conductivity detector TCD, and also mass spectrophotometric detector also used for the sensitive compounds, and also it will be used to identify the known compounds. For FID and TCD detectors, the compounds will be analyzed based on the retention time of the standard and the sample based on the obtained peak area. Then the mass spectrophotometric detector will work on based on the molecular weight of the compound, molecular mass of the compound. For the unknown molecules, compounds that tuned or eluted from the column will be ionized and the charged molecules will be estimated and quantified. For unknown molecules, the obtained probable mass will be compared with the NIST library and the compound will be identified and further quantified. So there will be a library based which will be giving a tentative identification of the compound based on the mass which is detected for the unknown compounds. So this is the future which is equipped in the mass detector in the gas chromatography. Now come to the method development in a gas chromatography technique. How you develop a method for a compound by using gas chromatography. First, you have to do the literature search. The information collected from the literature will be very useful for the method development. You should understand the boiling point of the compound because you are going to analyze volatile compounds which is mixed with the gas. So the compound has to get volatile when you use in this gas chromatography. Generally, The boiling point of the compound should be less than 80 degrees centigrade, for which we use a headspace autosampler where you can use the samples directly, and this is generally used for the very highly volatile organic compounds which is having low boiling point, and generally the organic solvents. If the boiling point is 80 to 200 degrees centigrade, you can use the auto liquid sampler ALS for the analysis. If the mixture of compounds will be analyzed through the ALS, and the temperature ramping modification will be useful for the separation of the compounds. So if there are several mix of the compounds need to be analyzed, you can use a temperature wrapping modification technique in the gas chromatography. During the method development, we should understand the nature of the compounds. So the polar nature of the compounds need to be known to select the column for the particular method. And the non-polar columns will preferentially retain non-polar compounds and give good resolution. The wax and polyethylene glycol columns are highly selective toward polar compounds such as alcohols. Then the most commonly used detector is FID, flame ionization detector, for sensitive molecules. And for more sensitive molecules or low quantity measurements, you can use the mass spectrophotometric detector, which we have already seen. Then the software used in the gas chromatography is generally Open Lab CDS or mp4 or lab solution based on the manufacturer of the gas chromatography instrument. In case of mass detector, you can use the mass hunter or mass link softwares for the instrument. This particular slide talks about the mass detector used in the gas chromatography, that is the GCMS system, which is generally used to identify and quantify various compounds. Here the fragmentation of the molecules generally by electron bombardment, then the separation is based on the charge ratio, that is mass to charge ratio. The commonly used technique for the ionization is electron ionization, and in this method you can use SIM method as well as the scan method. SIM method is for the quantification technique. It will accurately give the quantification of the molecule. Then the scan mode will be used to scan the compounds in the molecular range of 50 to 600 M by Z. Generally, as we already spoke about, the more sensitive molecules shall be analyzed using the mass detectors. Finally, coming to the calibration of the gas chromatographic instrument, it is calibrated for various parameters like flow rate accuracy of the carrier gas, injector precision, and detector linearity. The carrier gas flow rate accuracy will be measured by the set flow rate, and the actual flow rate will be measured and compared using the flow meter gauge. Then the injector precision is calibrated using 6 replicate injections of the standard like toluene, methanol, or linden. The percentage RSD, relative standard deviation of the retention time, and peak area shall not be more than 2 and 5 respectively. Then the detector linearity, different concentration of the standard will be injected and the peak area and concentration shall be compared. Then the correlation coefficient R value shall not be less than 0.99. So these are the few parameters which we need to calibrate time to time for the gas chromatography to get accurate results for the testings, and you are making sure that the instrument is working properly before the or during the analysis. Now coming to the pharmaceutical applications of the gas chromatography, there is wide range of applications. So basically we have seen that the volatile nature of the compounds is critical for the application of this particular method. So the first and foremost estimation of residual solvent in API as well as the finished product. The toxic solvents like toluene, methanol, ethanol, N-hexane, dichloromethane, etc. can be analyzed through this method in the API as well as finished product, so that these toxic solvents can be limited and controlled in the API as well as the formulation. Then also you can analyze various active pharmaceutical and ingredient as well as excipients which are volatile in nature, and also it is used for the analysis of castor oil, terpenes, and detection of narcotics, barbiturates, anticonvulsants, anesthetics, alcohols, etc. In medicinal chemistry, GCMS is used in the synthesis and characterization of the compounds in the pharmaceutical biotechnology. In other industries like food as well as plastic, petrochemical industries, it is used to separate the volatile mixtures, and it is also used for the qualitative and quantitative analysis of food products like volatile compounds, examples are clove oil, etc. And detection and analysis of contaminants such as environmental pollutants like pesticides and naturally occurring toxin can be measured using gas chromatography. Then quality control of chemicals in medicines, automobiles, etc. can be monitored. And the analysis of natural products, and also it can be used to detect the blood alcohol levels. And you can separate n number of hydrocarbons in petroleum by GLC technique. And also it is used to study the reaction mechanism of the chemical synthesis or chemical processes. So as per in this module, we have seen the gas chromatographic technique in detail, including the working process of the gas chromatography, different parts of the gas chromatography instrument, and the applications of the gas chromatography instrument and calibration of the gas chromatography instrument. In the upcoming modules, we will see some general method of analytical development, validations, extractable leachables, calculation methods, etc. Thank you.